So my name is Timon Ger. I'm from ETH Zurich. I'm a PhD student there. And this is joint work with Matthew, Dana, Peter, Svarat, and Martin. So as you all... All right, so as you all probably know, neural networks are not robust against input perturbations. So here we have three very nice images of roads, and as you can see, it's probably a good idea to go left here. But we have three neural networks, the yellow, a green, and the red one. And one of those, okay, I didn't press. Okay. And one of those actually disagrees and tells us to go to the right. And to be fair, somebody was a bit evil here and actually modified those images. So you can see some black patches, and those are responsible for those misclassifications. But of course, we don't want this because as humans, we can see you should go left. And there are many other ways to, okay. There are many other kinds of adversarial attacks on deep learning models. For example, you can actually impersonate someone else in like by just wearing some sort of funky goggles. And there's also attacks that, okay, there are also attacks that actually are not perceptible by a human. So here we have an image of a panda bear, and then we add some noise to it, and now the neural net is actually very confident that this is a gibbon. And there's been a lot of work on attacking neural networks, also some heuristic defenses that empirically improve robustness a little bit. But there's been less work on proving that neural networks actually do what they're supposed to do, in the sense of they don't behave differently on specific images if you just change the image a little bit. And in this work, we're trying to address this. Okay. And we want to prove that there are no robustness violations around a specific image. And what we want is we want a system that is automated and actually scales to real neural nets. So this is the problem statement. So we have a neural network. It maps inputs to outputs. Some of the outputs are possible. Some of the inputs are possible. Those are the inputs that the attacker can cause by perturbing a particular image, for example. And we have a safe set of outputs. So this could be all the outputs that classify to the same thing. And the challenge here is that X may contain a lot of inputs. So there are many possible attacks, and we need to defend against all of them. And existing solutions based on SMT actually do not scale to a large network. They work well for small networks, but if you have large neural nets, they stop working. And the key insight of this work is that we can use AI to analyze neural nets. And by AI, I mean, of course, abstract interpretation. And who knows about abstract interpretation? Okay, not a lot of people. So abstract interpretation is actually about 40 years old, which means that maybe it will become the next big thing soon. But it also means that it had a lot of time to develop, and what abstract interpretation actually is, and this will be the most technical slide of this talk. Okay, it's a theory for approximating program behaviors. So we have a program, and now we want to say, well, what can this program do? And we're satisfied if somebody tells us, well, it can do at most this. This means that abstract interpretation, it is sound, so if it proves something, it holds, but it's incomplete. It usually won't prove everything you can. And the ingredients for abstract interpretation are you have some abstract domain, and each element of the abstract domain represents some set. So you can think some geometric shape. And you have this gamma function that tells you which shape it represents. And then you have abstract transformers that preserve this approximation property. So if we have something that approximates A and we take the image through F, then the abstract transformer of F will give us something whose concretization is an over-approximation to the actual outputs. And abstract domains have some standard set of built-in operations. What we need are this meet operator, which just intersects given abstract element with some linear constraints. We have a join operator that combines two abstract elements and gives you back a combination. And we have an affine transformer, which is just an abstract transformer for an affine transformation. So there will be some more images. For example, this one. So what this shows is that there are actually different abstract domains. One of them is just the box domain. It's illustrated in blue. And this is what standard interval arithmetic will give you. So it will tell you the output is somewhere in this box. Then in green, we have the sonotope abstract domain. And a sonotope is just an image of an m-dimensional hypercube under some affine transformation. So it's some sort of symmetric polytope. And we have, okay. Can we go back once? Thanks. So we have the polyhedra domain, which is just some convex set. And we have 4 points here. The blue points, they are approximated. Then we apply some function, and we will get some other shape. And all the 4 points will still be in this new shape. And this is what abstract interpretation does. So now, what are neural nets? So neural networks are just some compositions of layers, and for us, each layer is either a fully connected layer, a convolutional layer, or a max pooling layer. And our goal will be to define abstract transformers for each layer type, because abstract interpretation is compositional. So if you can do it for 2 functions, you can do it for the composition. It may not be the best way to do it, but you can. So this is a high-level illustration of how abstract interpretation of neural nets works. We have an image of an 8, and we say, well, every pixel that is white, probably you can make it brighter, and you will still get an 8. And this will give you a number of different images, here represented by blue points, which you can over-approximate by this green abstract element. And then everything, can you go back? Thanks. Everything beyond that is the neural net. So we have a convolutional layer, followed by a max pooling layer, followed by a fully connected layer. And they will all operate on this shape and give you some other shape that over-approximates the result. So you have also some red points. Those are points that cannot occur in practice, but are included as possible behaviors by abstract interpretation. And the final property you will check on A4. Okay. So neural nets usually use this sort of ReLU activation, or the Moto nonlinear activation function. What ReLU does is just it picks all the neurons in a layer and caps them to 0. So if they're negative, the activations will become 0. Can I go back? Thanks. And the ReLU abstract transformer, therefore, just intersects. So it's a composition of n transformers, one for each of the neurons. And it just intersects the abstract element with these conditions that it's smaller than 0 or larger equal to 0. If it's smaller than 0, it will set it to 0 using the affine transformer. And this is an illustration. We have an abstract element, then we split it into 2. You can see that each of those 2 is an over-approximation to what you would get if you intersected actually with this constraint. Then we apply the relevant transformations to both of them and join them together in the end to get something that approximates both branches. And for other layer types, I mean, for fully connected layers, it's easy. So a fully connected layer is just an affine transformation followed by a ReLU activation. So we can just use the affine transformer, which is provided by the extra domain, and follow it with the ReLU transformer. Then there are also convolutional layers, and convolutions. So neural networks sometimes convolve a given layer with some multiple filters. And these filters are actually just linear functions, so we can obtain some sparse matrix such that this convolutional layer is actually equivalent to a fully connected layer, and then we use the same approach. And we also have max pooling layers, but in the interest of time, you can see in the paper if you're interested. We have implemented this approach. It was initially based on the Apron library. Now it's based on Elina, which is in-house. And what we've observed is that the sonotope abstract domain strikes a good balance between precision and scalability. So we've evaluated our approach, of course. So here you can see results on a convolutional neural network with a lot of neurons. we showed that the box domain is faster than the sonotope domain, and we have also tried polyhedra domain, but it was too slow, so it didn't terminate at all. This took less than 1 hour, but those results are out of date. And now we can do actually a little bit better than that, also in terms of precision. Then we've also compared to existing methods to certify things. So there are SMT-based methods that actually just solve a set of constraints and are complete in theory, but of course will time out. We have set a timeout of 1 hour here. And as you can see, Reluplex shows this sort of very exponential scaling, whereas with abstract interpretation, you don't see it that early. So we have here a sonotope domain. We have sonotope 64, which is the same as sonotope, but we keep up to 64 different sonotopes to get some more precision. And as you can see, our approach actually verifies more than Reluplex within this time limit of 1 hour. In the future, or actually right now, we're using abstract interpretation to train the neural network. And we are adding support for more activation functions, so not just ReLU, but also sigmoid and 10H. And we are improving the abstract transformers by specializing them to the abstract domain. So everything you've seen today is very generic. We can actually do better by doing abstract transformers directly for the sonotopes. And we're also deriving data parallel abstract transformers. So to summarize, neural networks are not robust. We can use abstract interpretation to show that for specific images, you cannot get the adversarial perturbations. We have defined abstract transformers for common layers, and our approach is quite precise and scales. So I will be happy to answer questions, also offline if you like. Thank you very much.
Okay, we have some time for some questions. And I'd like to start with one question. So you said that this type of analysis is obviously not complete. So based on your experience, what are some examples where this approach fails to find a proof?
Well, they are all in the paper, actually. So we have improved the approach now, and for some of the benchmarks, we can actually now prove 100% of them. So basically, the takeaway is that you can get more or less precision based on what your abstract transformers are.
I think we have a question there.
Hi, thank you very much. Very interesting work. So I have a question about the evaluation. It shows that this seems only a one-layer convolutional neural network. Right? Have you tried larger networks?
This was just an illustrative example. This is not what we evaluated on. So what we evaluated on actually has a lot of layers. We had feed-forward neural nets with 9 layers, for example.
I see.
And the convolutional net, I don't really remember how many layers it had, but I think like 6 or something.
Can you go back to one slide? Okay. So for the experiment, I didn't hear clearly. So what is the data set are you using?
Sorry?
What is the data set?
The data set,
right,
yes,
right.
Very good point. So it's MNIST and CIFAR10.
Oh, thank you.
All right, then if there are no more questions, then let's thank the speaker.